Hi everyone, in this video, I will introduce our work, orthogonal Jacobian regularization, for unsupervised disentanglement in image generation. For a disentangled representation, each dimension should control the change in one factor of variation, while being independent of changes in other factors. Our method is based on the straightforward intuition, when perturbing one dimension of the input, the change in the output should be independent of those caused by the other dimensions. We use the Jacobian vectors to represent the change caused by the latent inputs. To encourage independence among them, we let them be orthogonal. Considering all the dimensions, we introduce our orthogonal Jacobian regularization, which we also call OROJAR. Calculating the above OROJAR is time-consuming. To accelerate training, we approximate it by variance over the inner product of the first directional derivatives, using Hutchinson's estimator. Here the v vectors are random Rademacher vectors. The first directional derivative can be computed by first-order difference approximation. We then introduce how to apply our OROJAR to generative adversarial networks. In GANs, generator is usually trained with the standard adversarial laws. After adding the OROJAR, it will encourage the model to be disentangled. Besides, we can also use OROJAR to discover meaningful latent directions in a pre-trained GAN. Specifically, we introduce a learnable matrix A. Each column of A is a direction, and it can be used to edit the generated image. Omega is a one-hot vector indexes the column of A, and eta is a scalar that controls how far z should move in the direction. A can be optimized by following equation. OROJAR is now taken with respect to omega instead of z. We first use the edge shoes datasets to evaluate our method. It consists of both edge images and shoe images, and we mix them to train the GAN. As shown in the video, OROJAR learns to control the shape, style, and openness of the generated shoes. We also compare our methods against some state-of-the-art methods. CIFA fails to disentangle the shape with style. For example, when changing the style, the shape also be changed. Hashim penalty learns similar representations with ours, while our method covers more diverse shapes. We also compare our method on Claire complex dataset. It contains two objects, and each object has 5 factors, e.g., x and y position, shape, color, and size. From the video, our OROJAR controls the shape and color of each object independently. On the contrary, Hashim penalty tries to control the color of 2 objects with one dimension. Besides, when changing the shape of one object, the shape or color of another object also changes. CIFA also fails to disentangle the color and shape of each object. More qualitative results can be found in our paper. We also evaluate our method quantitatively. As shown in the table, our method achieves better disentanglement performance, which demonstrates the superiority of our method. As mentioned, our OROJAR can discover the meaningful directions of pre-trained GAN. Here we apply it to pre-trained big GAN. As shown in the video, our OROJAR can discover several disentangled directions, such as rotate, zoom, and color. Finally, we conduct an ablation study on the price to show the effectiveness of our OROJAR. We first apply it to each intermediate layer, and found that earlier layers are more effective in deactivating the redundant dimensions, resulting in better disentanglement. We then apply the OROJAR to the first multiple layers, and found applying OROJAR to the first multiple layers helps learn a better disentangled model. In conclusion, we propose an orthogonal Jacobian regularization to encourage generative model to learn disentangled representations. Jacobian matrix is used to represent the change caused by the latent input, and Jacobian vector of each dimension is constrained to be orthogonal to encourage disentanglement. Experimental results demonstrate that our OROJAR is effective in disentangled and controllable image generation, and performs favorably against the state-of-the-art methods. Thank you for watching. Please check our paper for more details.